Hello guys, welcome to another video and happy new year to you all. In this particular video, we're just going to take a quick look at what progressive waves are. So without wasting so much time, let's see what we've got here. Now, progressive waves, they're waves that transfers energy from one point to another without transferring the medium itself. So it's more like the particles, they're not really moving, okay, they're not changing position, but it's just the energy that comes with it. So all you see when you look at water waves and the ripples, going, it's not like the water particles are actually moving, but it's just there's a transfer of energy from one point to the other. And there are some basic things here. Displacement, that's a vector quantity, and that's the distance of a point on the wave from its equilibrium position. The equilibrium position is this point you have here. That's the point where the wave tends to come to a rest. So the displacement can be either upwards or downwards. If it's upwards, we refer to that as crest. If it's downwards like this, we refer to that as trough. Now, each of these, they have different lengths. Now, the maximum displacement is what we term as amplitude. That's what you have right here. Down to wavelength. Wavelength basically is the distance between points on successive oscillations. Okay, so this is a point in the wave, okay, and then all the way down here and all the way down here. Wavelength basically is the distance between points on successive oscillations of the wave that are in phase. Okay, so here now you've got the wavelength is from this crest to this crest. In some cases you might have waves that has two troughs, okay, and here would be your wavelength. Okay, so let's talk about period. Let's talk about period. Basically, period is the time taken for one complete oscillation or cycle. So from here to here, that's one complete oscillation. That's what we term as wavelength. One cycle. What's the length of that one cycle? That's the wavelength. Now, what's the time? Okay, how much time do we have on our hands for that wavelength, for that oscillation to occur? That's what we term as the period, and that's what you have right here. So the time it takes for this wavelength to happen is what we term as a period, and that's one oscillation. You got that right here. And the basic thing you need to know here is the equation for period. We have two variations. The first variation is what you have here as the frequency equals 1 over t. The frequency, if you don't know what that means, is just basically the number of oscillations per unit time. The number of, like in 1 second, how many oscillations do you have? So the shorter the wavelength, the more the oscillations you have per second. We'll get to that in a minute. So the basic equation you have here is just F, that's the frequency, which is measured in hertz, equals 1 over period. Period is measured in seconds. And if you flip these, it also means period equals 1 over frequency. It's as simple as that. And that means that if you increase the frequency, the period will reduce. If you reduce the frequency, there will be an increase in the period, and that's what we term as inverse proportion. That's the mathematical term we use when you have two variables moving in opposite directions. We've got the wave equation, and that's the speed of the wave equals frequency times the wave length. And that's basically what you have here. The speed, that's the sine v, and that is measured in meters per second. Or in some cases, you have it written as raised to the power of -1. Indices, when you take this guy upwards, that's 1 over x equals x raised to the power of -1. The law of indices is there. So that's just by the way. The speed has a relationship with the frequency and the wavelength. So let's do something here. the speed is directly proportional to the wavelength. The speed is also directly proportional to the frequency. So the more the wavelength, the more the speed. Okay, and the more the speed also, the more the frequency. So depending on which one you're keeping constant and which one you're toggling. All right. So that being said, that's a direct proportion. That's a direct proportion. And you can always, let's go back. You can always flip this, guys. If you make frequency the subject, that would be V over lambda, and that would also give you a new relationship between frequency and the speed. So that means the higher the frequency, the higher the speed, and an inverse proportion with the wavelength. The higher the frequency, the lower the wavelength. Let's talk about the relationship between wavelength and frequency. You know, I talked about that in the previous slide. Here you've got a very short wavelength. The crest, they're really close to each other, and the wavelength is just small. And then let's count. How many cycles do we have? We've got 1, 2, 3, 4. We've got 4 cycles here. We've got 4 cycles. So 4 cycles in this particular diagram, and the wavelength is low. All right. What if we have a large wavelength? How does that affect the frequency? Here, the wavelength is higher than what you have here. You can see larger than what you have there. And what that means at the frequency is that the frequency will be low. Here we just have 1 cycle, okay, which we can call 1 hertz, because frequency is measured in hertz, just hypothetically speaking. So the frequency is low right here, but the wavelength is large. The other one, the wavelength is low and the frequency is large. So that will be all for this video. I don't want to make it too long so you guys can grasp what we're saying. So thank you very much, and I'm going to see you in the next round of videos.